All right, so in this second of our two-part video series on equatorial waves, we're going to talk about how those characteristics that we described in our first video, especially their connections to deep moist convection or thunderstorms, are able to be used to identify them and monitor them utilizing data sets such as those derived from satellites or from numerical models. So again, when we introduced our wave structures in the previous video series, we showed that there was a unique location for each of the three wave types where convergence at low levels was maximized. And this location is where thunderstorms preferentially form. So we can see here in these two satellite images from 2002 with an equatorial Rossby wave here at left and a mixed Rossby gravity wave here at right, where we have thunderstorms preferentially found with those features. In this case, with the equatorial Rossby wave, we see it with the twin vortices here over the Indian Ocean, as well as out here in the Pacific Ocean, where we're inferring that there must be an area of high pressure mirrored about the equator between them. And for the mixed Rossby gravity wave, we see that it's slantwise across the equator. This one here to the east, we can't see the other side. It gets too far out of the satellite's view. But we can see at least this one here in the western part of the Pacific, that it's located here. So we know that our Kelvin wave moves to the east, and our equatorial Rossby and mixed Rossby gravity waves move to the west. Thunderstorms always lag behind those directions of motion relative to the area of low pressure. So a Kelvin wave that's moving toward the east is going to have thunderstorms preferentially to the west of the area of low pressure as it progresses along. For mixed Rossby gravity waves and equatorial Rossby waves that move off to the west, they're always going to have thunderstorms preferentially to the east of their areas of low pressure here. So we can use this information. Where the convection is maximized, is it on the equator or across the equator symmetrically or across the equator anti-symmetrically, as well as other information about the scale of these waves, 1,000 to 2,000 kilometers in terms of their wavelengths, as well as their directions of propagation and their return periods. How frequently would we expect the thunderstorm signals associated with these waves? What scale would we expect to see them on? And so on and so forth. That information can be used to help identify them through archived as well as real-time satellite data, as well as model outputs that look a lot like satellite data as well. So this requires that we give a very basic, very high-level overview of what are known as Fourier transforms. So we can take any continuous function, or really any data set, in this case something that extends around the entirety of the globe, around the entirety of the Earth near the equator. So let's say that we're looking at satellite-derived outgoing long-wave radiation. We introduced this in our earlier video series, and we talked about how that's closely related to thunderstorm activity. If you have deep thunderstorms, they're trapping a lot of radiation and re-emitting it back toward the surface. So there's less that goes to outer space as compared to clear skies where there's really nothing to trap it from being able to escape to outer space. So if a satellite is providing us outgoing long-wave radiation information, we know where thunderstorms are generally occurring at the time and in the places that the satellite image covers. So we have that data set, and it varies in space and it varies in time from one image to the next. So we can take those data and apply a Fourier transform and come up with a mathematical function that says that they're an infinite sum of waves with varying frequencies if we're looking at data that only vary in time, or varying wave numbers if we're looking at data that only vary in space, or both of them if we're looking at data that vary in both space and time. So basically what this is doing is taking atmospheric data around the globe, in our case outgoing long-wave radiation, and it's taking the temporal variation of that and the spatial variation of that and trying to identify what time periods, the frequencies, and what spatial scales, the wave numbers, have the strongest signal. We hypothesize that the convection or the thunderstorm signals associated with our equatorial waves will be those that have the strongest signal in this analysis. How we extract that, we'll go into a little bit more detail as we keep going here. So again, each frequency corresponds to a specific time interval. Remember, frequency is inversely related to period. And each wave number corresponds to a specific spatial distance or wavelength. Recall that those two are inversely related to each other as well. So again, this Fourier transform is providing information about how much of a signal exists within our data on these time periods and at these spatial scales, at these frequencies and at these wave numbers. So if we take multiple days or multiple years, many thousands of satellite images, and be able to extract out, all right, what scales are thunderstorms typically separated by? What time periods do they typically repeat in a particular location? The Fourier transform can provide us that information. And as we'll show, a lot of that signal that shows up is uniquely associated with our equatorial waves. So let's talk about what a Fourier transform looks like in a very basic, very generic sense here. So we're starting with a bell curve or a Gaussian wave here, and it's given by this black line that I have depicted here. There's an equation that allows us to specify that line, and we can assume that this domain from the left side of the plot to the right side of the plot, we can take that to be the entirety of the Earth around at the equator. So there's a peak here in the middle, and then it goes back to 0 on either side of that. I can use a Fourier transform and take that data set and write it in terms of a bunch of different terms. One that has wave number 0, one that has wave number 1, wave number 2, wave number 3, so on and so forth, all the way until the highest possible wave number with the shortest possible wavelength. So what I have depicted here in the gray, red, blue, purple, and then the darker gray dotted lines here is the output from doing that, but only keeping wave number 0, so no ridge trough across the entirety of the globe. Wave number 1, 1 ridge and trough across the globe. 2, 3, and 4, 2 ridges and troughs, 3, 4 ridges and troughs across the globe. And those are what are plotted here. So our wave number 0, this dot dashed line here, is a straight line with an amplitude of about 25. Wave number 1 in red has 1 trough at either end and the ridge here in the middle with a peak amplitude of about 35 or so. Our wave number 2 in blue has 2 ridges, one at the end and one in the middle, and 2 troughs on the either side of the ridges. Wave number 3 in purple, 3 ridges and troughs. Wave number 4 in the dotted line, 4 ridges and troughs. In this example, the amplitude is highest at wave number 1 and goes down as we go to higher wave numbers. The depiction here that I've just brought up on the right also has that initial bell curve or Gaussian wave here with the black line that's laid underneath a green line that we'll talk about here in just a moment. So in this case, I've also transformed into Fourier space, into, in this case, wave number. But I'm also then bringing it back to physical space by filtering the specific wave numbers that I'm interested in. In the red dashed line, that's wave numbers 0 and 1. In the blue dashed line, that's wave numbers 0, 1, and 2. And then 0 through 3, 0 through 4, and 0 through 8 as we get to those other lines. In this case, 0 through 1 is just the addition of this gray dashed line, dot dashed line, and this red dotted line here. So you get 1 wavelength across the domain. Wave number 2 is the gray dot dash, red dotted, and blue dashed lines all added together. 0 through 3 in purple are the gray, red, blue, and purple lines added together. 0 through 4 is all of these added together, and 0 through 8 would add the 5, 6, 7, and 8 wave number lines to that as well. So we can see that as we add more and more wave numbers to what we have here, we get a curve that looks a lot more like the actual physical solution, the actual bell curve or Gaussian curve. 0 and 1 aren't enough. 0 through 2 gets a little bit closer. 0 through 3 starts to get pretty close. 0 through 4 in the gray dotted line is very close. 0 through 8 in this case is almost a perfect match here. So what this depiction here at left is telling us is how much signal is associated with each of those wave numbers by their amplitude. If we were to look at different features, it wouldn't necessarily be that wave number 1, a very long feature, has the highest amplitude. Maybe it's wave number 50 or 70. But this generic example helps us to show how we can take any feature, in this case a Gaussian wave, and in the real atmosphere outgoing long wave radiation data, and separate it out into different scales of features that all add back together to give you your full data set, your full feature. So with all of this in mind, we want to fill in the gaps. How can we use Fourier transforms and those methods to be able to identify equatorial Rossby waves? Well, we know from theory that each equatorial wave type that we've considered has a unique propagation speed, some move faster than others, a unique period, some repeat more frequently than do others, propagation direction, a couple of them move to the west, one moves to the east, and horizontal scales. A couple of them are about 1,000 kilometer wavelength, one is about 2,000 kilometer wavelength. So we have information about that is time related, propagation speed, period, and to lesser extent propagation direction and scale. We have information that is almost exclusively wavelength or spatial dependent, propagation direction and horizontal scale. So we have data and we have waves that vary in time and in space. Fourier transforms allow us to identify signals in time and space. And so they're well suited to identifying equatorial waves from satellite data or model data using Fourier transforms. So we'll consider how this can be done on two separate timescales. One will be climatologically, and that's what we'll do first. We'll take many years, decades worth of data, and apply this to test the hypothesis that our strongest signals will be associated with equatorial waves. And we'll also do this in real time using a much shorter data period, often on the order of days to weeks, to show how we can take data that you would see right now and identify equatorial waves just from those noisy data sets. So we start climatologically here, and this chart is relatively complex here, so let me try to orient us. Along the y-axis in each of these charts is temporal information. You have the period in days, and you have the frequency, one divided by the period here on the y-axis. Frequency goes up as you go up along the y-axis. Period goes longer as you go down the y-axis. Remember, the two are inversely related to each other, so they should orient oppositely on this y-axis. So we're looking at periods from about 2 days to over 50 days here along the y-axis. Along the x-axis, we have wave number, ranging from -20 to +20. So the significance of negative versus positive values here is that negative are associated with features that are moving along the negative x-axis to the west. Positive values are ones that are moving along the positive x-axis or to the east. So this x-axis is giving us information about which direction they're moving, as well as the standard wave number information about how large of a scale they are. So where they are positioned on the y-axis tells us something about their period, and to lesser extent their propagation speed. Where they are positioned along the x-axis tells us something about the direction that they move and how large of a scale they actually are. Antisymmetric here on the left image is for features that have convective signals that are slantwise or different from one hemisphere to the other at a given longitude. That would be for our mixed Rossby gravity waves. Symmetric, however, is when they are either centered on the equator, like for our Kelvin waves, or symmetric across the equator at a given longitude, like for our equatorial Rossby waves. The color shading that you see here is a measure of how much signal is at a given wave number and frequency. So our strongest signals are associated with our equatorial waves, which I've indicated here in purple, and we see boxes for each one of them here. In the antisymmetric, it's our mixed Rossby gravity wave. Negative values of wave number indicate that they are moving to the west, and they are in periods roughly from about 7 days down to about 3 days here. So 3 to 6, 3 to 7 days in keeping with our original theory, antisymmetric in nature. That same region has very little signal on the symmetric side, as we would expect given the structure of mixed Rossby gravity waves. Whereas Kelvin waves here, in this green shaded region, have positive values of the wave number signal, so they're moving toward the east. They have wave numbers from about 2 on up to roughly 10 in terms of the most power. So that's a measure of their horizontal scale. They're very large scale features. And they have periods ranging from not quite 20 days down to about 2 to 2.5 days, 3 for the maximum signal. We said that Kelvin waves are more on the shorter end of this period range, but there is a spectrum of Kelvin waves that exists within the atmosphere, as this signal would indicate here. Finally, we have our equatorial Rossby waves depicted here, where they are in the symmetric side, as we would expect. They have negative values of wave number, as we would expect for features moving to the west. Also relatively large scales, about -2 to -10, so 2 to 10 waves across the globe, corresponding to thousands of kilometers. And these have very long periods and low frequencies, roughly about 10 days to over 20 days here, again matching our theoretical expectations. But there are also other modes of tropical variability or other forms of tropical variability that show up here. With the Madden-Julian oscillation, very small wave numbers, very long periods, and very small positive wave numbers indicating that it moves to the east, very small wave numbers meaning that it's very large scale, thousands of kilometers, and very long periods. This is sort of the so-called 45-day oscillation, and we'll discuss this more later on in the semester. We also have tropical disturbances here, TDs. These can be tropical waves, these can be tropical cyclones, they can be a number of different things. There's not a lot of power in either the antisymmetric or the symmetric side here, but these are smaller scale features, wave numbers of about 6 to 20, so hundreds to thousands of kilometers. They have periods of about 2.5 to 5 days, so they can recur relatively frequently. And they are on the negative side of the chart in both the symmetric and the antisymmetric side, meaning that they typically move from east to west within the tropics. We'll talk more about those types of disturbances later on in the semester as well. But the take home from this is that the strongest signal, the color shading that we see on the antisymmetric and the symmetric sides here, correspond primarily to our equatorial waves, which mean that if we can take data, transform them into this wave number and frequency space, and identify just these wave numbers and just these frequencies associated with each wave, and then bring that data back to physical space, we can take noisy atmospheric data that have a lot of variability in them and extract out the component that is uniquely associated with each one of those wave types. So yes, as we just noted, equatorial waves do show up in the satellite data with the unique frequencies and wave numbers that we saw from theoretical expectations before. We can use this information to identify and track them in real time. Take our outgoing long wave radiation anomalies, convert them into Fourier space. So instead of being varying in X, Y, and time, they vary in frequency and wave number. We then filter out only the frequencies, so only the periods, and only the wave numbers, the horizontal scales and directions of propagation, for a given wave. And then we use an inverse transform to bring that back to physical space and plot up the result. So here we have a depiction of total outgoing long wave radiation anomalies here in the top panel. The warmer colors, yellows, oranges, and browns, are higher outgoing long wave radiation. So this is where it's relatively cloud-free. The cold colors, blues, purples, pinks, and reds, are where you have negative outgoing long-wave radiation anomalies. So this is where it is relatively clouded over, relatively high thunderstorm activity, because there is less long-wave radiation that is escaping to outer space. So there's a lot of structure and a lot of detail to this data that we see here at the top. We can filter that using the Fourier transform, and we have 4 different panels below this. We'll ignore the top one, the Madden-Julian oscillation, because we're not discussing that here at this point. We have our equatorial Rossby wave here in the second panel, Kelvin waves here in the third, and mixed Rossby gravity waves here in the bottom. So we take these data, Fourier transform them, and keep only the frequencies and wave numbers associated with the equatorial Rossby, only with the Kelvin, or only with the mixed Rossby gravity wave, and then bring those back into physical space. And we get these much smoother looking plots that we see in the bottom panels. So we can kind of trace this negative anomaly for outgoing long-wave radiation centered on the equator over Africa. And we have a Kelvin wave associated with enhanced convective activity in the analysis as well. Likewise, this suppressed region near the equator in the Indian Ocean is associated with a suppressed phase of a Kelvin wave with reduced convection, reduced thunderstorm activity. Likewise, here near the international dateline in the Pacific Ocean, we have enhanced convective activity north of the equator with suppressed convective activity south of the equator. This corresponds nicely to a mixed Rossby gravity wave with enhanced activity north and suppressed activity to the south of the equator. We could then back out because we know where the thunderstorms are forming and not forming in these cases. We can tie that back to the structures of these waves. Where would we expect to see the areas of high and low pressure, cyclonic and anticyclonic flow in association with these features? So these are nice in that they're really honing in on those signals. It's not without caveats. There are other features that have similar scales and move at similar speeds as compared to these equatorial waves, especially when you get out of the equatorial regions. But nevertheless, these are doing a really good job of honing in on those features specific to the tropics. We can look at this in terms of a temporal progression as well. We have Kelvin waves here at the left and equatorial Rossby waves here at the right. So this is data for December 7th, 8th, and 9th, 2008, and then forecast day 1 for the 10th, day 2 for the 11th in 2008. So we're looking at a 4 to 5 day period here, and we have 2 different Kelvin waves. And in specific, we have the thunderstorm active portion of the Kelvin waves between the areas of high and low pressure where the winds are converging and facilitating thunderstorm development. One here over Western Africa that progresses to the east across Africa and ultimately dampens somewhat as it reaches to the Indian Ocean. Then we have one here on the west edge of the maritime continent, the far eastern edge of the Indian Ocean, that progresses to the east over the course of the next few days. So these black arrows are indicating the progression to the east or to the right as you go through time over the course of this 4 to 5 day period. Likewise, for equatorial Rossby waves here, we have an equatorial Rossby wave packet here. And in particular, we have enhanced convection on either side of the equator near the western end of the maritime continent, suppressed thunderstorms near the central to eastern portion of the maritime continent on either side of the equator, and then enhanced thunderstorms on either side of the equator near the international dateline. This is a 3-day average, December 7th through 9th. And this is a 3-day forecast average. And we see that these features, enhanced, suppressed, and enhanced thunderstorm activity, move slowly to the west. And thus these black arrows slant down and to the left on this diagram here over time, matching our expectations from the earlier analysis and theoretical information. Finally, we can often use what are known as Hofmöller diagrams. So these have 2 dimensions. Time is their y-axis, and longitude is their x-axis. So we're often averaging over latitude to give us just a single line of data in the x direction, so that we have just longitude in the x-axis here. And so we can see the time and space progression of data using these Hofmüller diagrams. So these are frequently used to monitor equatorial waves and outgoing long-wave radiation data. So the color shading that you see here on this diagram, this is a period of time from December 22nd, 2019 to April 12th, 2020. And we'll pay close attention to the December 22nd, 2019 through March 15th, 2020 period here, because that's based off of satellite data, whereas below that it's based off of model data, which is just a forecast rather than an actual analysis. The green areas are negative outgoing long-wave radiation anomalies, so enhanced thunderstorms. Green, think moist, wet rain. The brown is associated with enhanced outgoing long-wave radiation, positive outgoing long-wave radiation anomalies. So think relatively dry, cloud-free conditions. So it's a very noisy data set that varies in space across the x-axis and varies in time across the y-axis, and in this case averaged between 5 south and 5 north. We can filter these data to identify all sorts of different types of features, and in this case they've done so to identify 4 features. 2 equatorial wave modes, Kelvin and equatorial Rossby wave. Because we're dealing with symmetric data across the equator, we can't get our mixed Rossby gravity wave out of this. We have the Madden-Julian oscillation and then a low-pass filter, which is looking at very long-term variability, generally associated with the El Nino Southern Oscillation that we'll discuss later this semester as well. But for now, we'll focus just on these blue and these red contours here. So we take these time and space varying data, run the Fourier transform on them, keep only the frequencies and wave numbers associated with each of those 2 wave types, and then transform the data back. And so the contours that we have here in blue and in red are outgoing long-wave radiation anomalies, here at 16 watts per meter squared for each contour, associated with just the Kelvin wave or just an equatorial Rossby wave. So for instance, we have a series of Kelvin waves starting here around January 5th and moving toward the east as you go down on the chart in time. Here, January 5 to 19, about January 22nd to about February 2nd. And then we have another couple here that show up really nicely from late February, sort of like February 23rd or so, through to about the start of the pandemic, March 10th, give or take. So these features are moving quickly and to the east. So we see that they cover from about 30 degrees east longitude to roughly the international dateline over the course of about a 2-week period. Whereas equatorial Rossby waves here in the red, this was the enhanced phase. There's some dashed lines here and here that are the suppressed phase of an equatorial Rossby wave. They slope down and to the left. So as time increases going down, they're moving further to the west. And they move somewhat more slowly than do the Kelvin waves. This case here starts out around the international dateline on December 22nd. And then almost a month later, it is around 60 degrees east. So moving about the same distance as a Kelvin wave in twice the amount of the time. So note these different slopes, both in terms of the direction that they slope, as well as their steepness. Note how frequently they repeat. The Kelvin waves are pretty periodic here, every 2 to 3 weeks, give or take, in terms of where they are repeating in a given location. Equatorial Rossby waves are a little bit more sporadic in terms of where they're repeating. They're most common here in the Eastern Hemisphere rather than the Western Hemisphere. The reasons for that are largely beyond the scope of the class that we were going to consider here. But these are very rich images. You'll get experience working with these in one of the discussion questions for this material, as well as in terms of one of the homework assignments coming up later on in this semester. But I would encourage you to take stock of this, wrestle with this, think through what I've just discussed here, bring questions to class, and we'll talk through this in more detail as well. So this wraps up our discussion about equatorial wave monitoring and identification. From here, we're going to move next week into a broader discussion of other tropical circulations. We're going to look through to our Hadley cell as well as other circulations like the Walker cell, and then into other ways in which those vary with time. We'll see these equatorial waves, however, show up consistently with different structures, different combinations of them as we go into all of those other circulations. But for now, that's it in terms of equatorial waves.